Every AI model you've used, GPT, LLaMA, Stable Diffusion, learned by solving one giant math problem. That problem is finding the best possible parameters for the model. To be precise, training means finding a set of parameters called theta that minimizes a loss function L of theta. The loss is the average mistake the model makes across every training example. Smaller loss means better predictions. Now GPT-3 has 175 billion parameters. That means theta lives in a 175 billion dimensional space. We can't visualize that, so we picture a two-dimensional slice of it as a mountain range. Each point on that surface is one possible setting of all the parameters. The height of the surface is the loss. High means the model is wrong. Low means it's right. The surface is called the loss landscape, and it's anything but simple. It's non-convex, full of hills, valleys, ridges, and vast flat plains. There is no single obvious bottom. Many valleys compete, and some are traps. So why not just solve for the best theta directly with algebra? For a simple linear model, there is a closed-form solution. Theta star equals the inverse of x transpose x multiplied by x transpose y. But inverting that matrix costs order n cubed operations. At 175 billion parameters, that computation is completely out of reach. And for deep networks with ReLU activations, there is no closed form at all. The only practical option is iterative. Take small steps guided by the gradient. Here's the key insight. The gradient of L points in the direction of steepest descent, so we step in the opposite direction to go downhill. The update rule is one line. Theta gets updated by subtracting the gradient, scaled by a small number called the learning rate. Repeat that step millions of times and the model learns. But the landscape makes this far harder than it sounds, and that's exactly what we'll dig into next. In this part, we look at how gradient descent works and why training at scale demands something noisier. The simplest version computes the gradient over your entire dataset in one shot. That gradient is exact, but on ImageNet's 1.2 million images, one step means a full pass over them all. At web scale, with trillions of tokens, that's hopeless. So, in practice, we sample a small random mini-batch and step on that estimate. For vision, a typical batch is 32 to 512 examples. For large language models, it's thousands of tokens per GPU per step. The gradient from that mini-batch is noisy, a rough estimate of the true gradient. And the key insight, that noise is a feature, not a bug. A noisy gradient helps escape saddle points where the exact gradient is zero. It also tends to land in flatter regions that generalize better, shown empirically by Keskar and colleagues in 2017. One epoch is one full pass over the training data. A step or iteration is a single mini-batch update. Steps per epoch equals dataset size divided by batch size. With 1 million examples and a batch of 256, that's roughly 3,900 steps per epoch. The most important knob here is the learning rate. Set it too large and the parameter ball bounces over valleys and the loss diverges. Set it too small and it barely moves, stalling on plateaus. You might think the main enemy is getting trapped in a local minimum. In high dimensions, local minima are exponentially rare. Dauphin colleagues showed this at NeurIPS in 2014. In n dimensions, the probability that any critical point is a true local minimum is 1/2 to the power n. It vanishes fast. Nearly every flat spot is a saddle point, a minimum in some directions, a maximum in others. The real obstacles are saddle points, narrow ravines, and long flat plateaus, not local minima. That's the messy reality SGD must navigate. Next, we'll see how momentum makes the walk far more purposeful. In this part, we look at momentum, a simple idea that makes gradient descent much faster. So far, every update looks only at the current gradient and forgets the past. Momentum, introduced by Boris Polyak in 1964, changes that. Instead of jumping straight along the current gradient, you accumulate a velocity vector, a running weighted blend of all past gradients, and move the parameters along that, not the raw gradient. The standard decay factor beta is set to 0.9. At beta equals 0.9, the velocity effectively averages over the last 10 gradients. Think of a heavy bowling ball rolling downhill. It has inertia and doesn't snap to a new direction when the slope changes. Where the gradient keeps pointing the same way, the ball builds up speed. Where it flips back and forth, the contributions cancel and motion stays small. This is exactly what saves us in a ravine, a canyon-shaped loss surface steep across the walls, gently sloped along the floor. Vanilla gradient descent zigzags violently across the narrow walls and barely advances. With momentum, the side-to-side oscillations average out, while the consistent downhill component keeps adding up. The ball accelerates down the canyon instead of wasting steps on the walls. Nesterov Accelerated Gradient, published in 1983, adds one more twist. Instead of computing the gradient at the current position, peek ahead to where momentum is carrying you, then form the velocity update. The diagram shows that look-ahead position, theta minus beta times v. This tiny change lets the optimizer correct its course before it overshoots. On convex problems, the improvement is a proven rate change, not just intuition. Plane gradient descent converges at order 1 over t. Nesterov improves that to order 1 over t squared. Genuine acceleration, not merely smoother updates. Momentum is not a standalone trick. It lives inside nearly every modern method. SGD with momentum uses it directly, with the same beta 0.9 default, and Adam's first moment estimate is exactly a momentum term under the hood. Coming up next, we adapt the learning rate for each parameter individually. The story of AdaGrad and RMSProp. This part is about giving every parameter its own learning rate, automatically. Until now, every parameter shared one global rate, but not all parameters are equal. Some get large gradients constantly, others update only occasionally. The idea behind adaptive methods: let each parameter tune its own step size from its own gradient history. AdaGrad, published by Ducci, Hazan and Singer in 2011, was the first to do this cleanly. It keeps a running sum of squared gradients for every parameter. Call that sum G. At each step, the update for a parameter is divided by the square root of its G. So a parameter that has seen large gradients many times gets a much smaller effective step. A parameter that rarely updates, like an embedding for an uncommon word, keeps a large step. That's exactly what you want for sparse data. Frequent words get careful updates, rare words stay sensitive and keep learning. But there is a serious problem. G only ever grows, and it never shrinks. So every learning rate eventually decays towards 0, and training quietly stalls. RMSProp fixes this with one key change. Instead of accumulating the full sum, it uses an exponential moving average of squared gradients, so old history slowly leaks away. RMSProp was introduced by Hinton in 2012, notably not in a paper, but in a Coursera lecture slide. The decay default is 0.9, the learning rate is 0.001, and epsilon is 10 to the minus 8. Because old squared gradients fade out, the effective rate can stabilize or even recover instead of dying to 0. So AdaGrad turns the dial down and locks it. RMSProp turns it down but lets it rise again as the gradient quiets. This made RMSProp the go-to optimizer for recurrent networks, where AdaGrad stalled, and it stayed the default until the next breakthrough combined it with momentum. In Part 5, we will see how Adam fuses RMSProp's adaptive rates with momentum into one algorithm. In this part, we fuse momentum and adaptive rates into the algorithm behind almost every modern AI model. That combination is Adam, introduced by Kingma and Barr in 2014. Momentum and RMSProp fused into one rule, tracking two statistics per parameter. The first moment is an exponential moving average of the raw gradients, exactly momentum, with a default beta 1 of 0.9. The second moment is an exponential moving average of the squared gradients, exactly RMSProp, with a default beta 2 of 0.999. Both moments start at 0, so early values are biased too low. Adam fixes this with bias correction. Divide the first moment by 1 minus beta 1 to the power t. Divide the second moment by 1 minus beta 2 to the power t. At step 1, those divisors rescale the estimates back to full size. Then step by the corrected first moment divided by the square root of the corrected second moment plus epsilon. The full defaults from the paper. Beta 1 0.9. Beta 2 0.999. Epsilon is 10 to the minus 8 and the learning rate is 0.001. Adam has a subtle flaw. Standard weight decay goes inside the gradient, so Adam divides it by the adaptive term and heavily updated weights get almost no regularization. Loshchilov and Hutter identified this bug in 2017 and proposed AdamW. The fix is to decouple weight decay, apply it directly to the weights after the adaptive step. That makes regularization uniform, with a typical decay of 0.1 for LLMs. AdamW is now the default for essentially every transformer-based LLM. GPT-3, LLaMA, and Stable Diffusion all use it or a close variant. At the frontier, Lion from 2023 uses sign-based momentum at half Adam's memory. LAM from 2019 adds a layer-wise trust ratio. And Muon from 2024 uses orthogonal updates. Next, we look at learning rate schedules, warm-up, and real training configs. In this final part, we cover schedules, warm-up, and the configs that train real models. A fixed rate is never ideal. Too large early diverges, too small late never converges, so we change it over time. Warm-up is the first move. Linearly ramp the rate from near zero to its peak over the first 2,000 steps. Why do transformers need it? Early on, Adam's second moment starts at 0, so a large rate makes steps explode. Warm-up lets it settle first. After warm-up, cosine annealing decays the rate smoothly, like a car braking to a stop. The modern recipe, used by GPT-3 and LLaMA, is warm-up then cosine decay to 10%. Here is GPT-3's actual config. AdamW, beta 1 0.9, beta 2 0.95, learning rate 6e-5, weight decay 0.1, gradient clip 1.0. Beta 2 is 0.95, not the default 0.999, a shorter memory that reacts faster. LLaMA used nearly the same. AdamW, beta 2 0.95, weight decay 0.1, learning rate 3e-4 with 2,000 warm-up steps. For vision, it's different. SGD with momentum still wins for ResNets. ResNet 50 uses plain SGD, momentum 0.9, with step decay cutting the rate tenfold. Adam tends to converge to sharper minima on images, hurting generalization. Gradient clipping caps the gradient norm at 1.0, a speed limiter for rare bad batches. Cauchy described steepest descent in 1847. Polyak added momentum in 1964. AdaGrad in 2011 gave each parameter its own rate, and RMSProp fixed its fatal flaw the next year. Adam combined the two in 2014. AdamW fixed the weight decay bug in 2017. Lion and Muon push the frontier now. Each step fixed one failure of the last, yet the core idea never changed. Compute the gradient, step downhill, repeat. That humble idea scaled from Cauchy's notebook to the models reshaping our world.